Okay, hello
Okay.
everybody. Welcome back to the seminar series. Again, thank you very much, Lo and Giacomo, for organizing the seminars. And a special thanks at this time to the speaker, okay, Alessandro Betti. So just to very quickly, just to introduce Alessandro, and then the floor will be yours, Alessandro. So Alessandro Betti is working at the Artificial Intelligence Lab at the University of Siena. Very interesting place, a very interesting city indeed. And he actually has a very interesting background because by training, if correct me if I am wrong, Alessandro, is a physicist, okay, and with some obvious interest in things like symmetries and variational principles. That's why I invited him to give this talk, because we share this interest. And this is something that he will be talking about today. Other than that, he has also a quite interest in areas of artificial intelligence, obviously, and in particular computer vision as well. And yes, as an anecdote, if I may, he has actually a PhD from 3 universities, actually, from Florence, Pisa, and Siena, something that is very unusual, in the United Kingdom, but here, and so one final thing before Alessandro starts his talk on variational framework for laws of learning is that this meeting is being recorded, okay? So that you all are aware. So you don't want to be recorded on questions or whatever, please take this into account. So it's been recorded. And without further ado, Alessandro,
Yes. Thank you, Eduardo, for the nice introduction. And yes, today I want to talk to you about this idea of how we can come up with laws that are used for learning using variational principles. So before going to the main part of the presentation, I would like also to make some comments on the kind of data we are interested in, which is data that comes as a coherent temporal signal. And so the reason why we like those kind of data is because, other than being rather a natural way to define a learning problem, it also gave us the possibility to express and to write down some constraints that otherwise may be difficult to precisely state, some kind of dynamical constraints that I will talk a little bit more in the rest of the presentation. And then another interesting fact that we can exploit when we work with time, let's say, is that of course we can, in some sense, and in a way that I will make a little bit more precise in a minute, since we work with a one-dimensional parameter, simplify some kind of problem that usually can be defined in high dimensional feature space. Let me just spend some moments on this quite vague statement. So for definiteness, let us take in consideration a learning problems, a supervised learning problem that, as you know, it consists into the choice of some function, of some map, from an input space, which is generally high dimensional input space, to a space of label or of targets. And there are at least 2 approaches to this problem. And one is the approach that has been proposed some time ago in the learning community by Poggio and Girosi, which is the one that suggests to choose the function among other in a functional space based on their regularity properties. And the other approach would be that of choosing a parametric model and therefore define the learning in terms of the quest for the right parameters that here I indicate with W. Now, since we're interested in temporal environments, we may ask how these two different approaches have a time embedding. So the first approach would require, since you want to process information as it comes in time, to enlarge the domain of the function from which we are allowed to select the solution by giving an extra, let's say, dimension, which is the temporal horizon. And then we can impose also in this joint domain some regularity properties. The other one instead would be that of exploiting parametric model and to assume the whole temporal flexibility of the model can be captured by the parameter themselves. And so in this case, the learning problem would be that of choosing from some functional space, let's say, the map of the trajectory of the weights. That, of course, is something which, as domain, has a one-dimensional real value, which is the time. So, of course, the two approaches based on regularization both need to tackle in some way and to solve a problem which is in both cases defined over an input space that is is high dimensional input space. And as you may know, the problem there, as it came out very quickly in the literature, is that depending on the differential operator, for example, that you choose to impose this kind of regularity, and since you are in high dimensional space, you can choose, you have plenty of choice, then you can then you can have a quite strong bias on the kind of function that you can represent with that choice. While in the second case, so in the case in which you have, let's say, a parametric model, and you look for the trajectory of the weights, in that case, of course, the problem is a little bit complicated with respect to the plain problem of finding a finite number of parameters. But now we have the advantage that those functions are a function that lives in one dimension. So a little bit more, simpler problem. Of course, here you have to have a good hint on what model do you choose, and probably nowadays we can say that with respect to this point, machine learning is teaching us that neural network could be a very good candidate for many tasks in learning. So in the rest of the presentation, I will assume that we are working with a second scenario. So we have a fixed model that, if you like, you can think of it as a neural network. And what we want to do is we want to select a trajectory of the weight. So when I say laws of learning, so choosing or guessing laws of learning, I mean some mechanism by which we can select this trajectory of the weights. And in general, we would like to select this trajectory in such a way that at least these 3 points are satisfied. The first one being causality. And here by causality, I strictly mean some definition that is common in system dynamics, meaning I give initial condition and then I give a rule that tells me how to update that initial condition to get the solution at all times. The second requirement is temporal locality, which means that this rule can only look at near in time points. So if I'm at point T, in order to select the value of the parameters at that time, I'm only allowed to look at the values of the signal, the input signal, and previous values of the parameters nearby that time. And then the last assumption here is that the task, the learning task, I am assuming that is specified by some kind of loss function. So this being said, we can try to look at some rule which satisfy those requirements. So the first two requirements, that is causality and temporal locality, are satisfied if surely if we choose a Cauchy problem for an ordinary differential equation as our law for the development of the parameters. And of course, here we can look into what would happen if we choose Newtonian equation, so Newton's equation for classical mechanics to learn the parameters of a model, of a neural network, for example. And we quickly realize that, of course, for example, in batch mode, so when the potential does not depend on time, and when when we take the viscous limit, that is when we take the mass of the coefficient in front of the second order term in the equation to 0, what we end up with is the classical gradient descent rule. And again, in the same limit, in the same viscous limit, when we choose, for example, a potential that depends on time, which has, let's say, a specific temporal dependence, not any temporal dependence would do, as we know, but with carefully chosen temporal dependence, then in the same limits, we get what we know as a continuous version of a stochastic gradient descent, which is a very common approach, a very common method, optimization method in nowadays machine learning. Of course, once we have selected such laws for the development of the parameter, one caveat is that we always need to check whether the dynamics that we find is, of course, consistent with learning. So, for example, we might ask if the weights after some times have some kind of convergence because the system has been exposed to enough information to start to capture some kind of regularity. And indeed, this is a very important topic that is very, in its most general form, is very, I would say, open problem. But at least for some of the update rules that we have, it is a known. So there are some very good results. For example, for stochastic gradient descent and gradient descent, and we have also tried in our lab to tackle this problem, also in general for a second order differential equation of the kind that we see here, and we found that, for example, under some condition, repetitivity condition on the input, we have also some kind of periodic behavior on the weight, so some kind of convergence of the weights that tells us that when after some times when a pattern is repeated, then the value of the weight on that pattern is similar. But this is I would say something that we must keep in mind, but I won't be bothered with this in this seminar. I only wanted to bring this up because, of course, is one of the main point that one needs to have in mind. And this being said, we can start with the main, let's say, discussion that I want to bring to your attention, and is, of course, how can variational rules, how can variational approaches help into guessing or modifying or suggesting new ways of finding those trajectory of the parameters that I've been talking about. So the reason why we very much like these variational approaches is first of all because since I'm a physicist and we have seen that already Newton's law in some senses can be considered as a prototype of laws of learning because it very much is very close to gradient descent, stochastic gradient descent, and gradient descent with momentum term, if you want. This seems a very natural things to do. So to investigate from the side, let's say the variational genesis of those laws. And then because, of course, it is also very natural from a mathematical point of view, since the problem is the functional problem of determining a trajectory. This is exactly the setting that one should is expected to look into to find solution to these kind of problems. So as a starting point, let me begin with reviewing how Newton's law for a system described by a potential can be expressed in terms of a variational statement, so a functional statement, if you want. So typically what it is done in classical mechanics is to state Newton's law in terms of Hamilton principle by defining a functional, which is usually called the action, which here is identified with this capital S, which consists of an integral, so is an integral functional of a kinetic term minus a potential term. And this is what is called the Lagrangian. And typically, one may say that the solution of the equation for Newtonian mechanics of a system that is described by potential U coincide with the extremal of this function. So now, this statement is not very precise as it is, mainly because it fails to tell you where what is the domain of this functional, and which is very important information even for defining what let's say a stationary point is or an extremal is. So more precisely, Hamilton principle states that the solution of the equation of Newtonian mechanics x bar coincide with the stationary point when, of course, they are unique of the action defined on this set. And you immediately see that the set X, that here I've called X, other than, of course, giving some regularity constraints on the solution, and here we can discuss about this, but the crucial point is that in order to precisely have these equivalence between stationary point of a functional and the solution of Newton's equation, you have to impose some boundary conditions. So you are basically saying, you are basically fixing the endpoints of the trajectory. And this, of course, ruins our, let's say, one of our requirements, that is causality. And the other point, which we still don't like in this formulation in order to be used to generate or to guess new learning rules is the fact that as it is, so if you look at this functional, as it is, it does not include dissipation. So this issue about this dissipation, it turns out that can be quite easily be solved by still remaining in the same framework by modifying the Lagrangian, and adding this exponential factor in front of the Lagrangian, this e to the theta t. And this factor, when you do the variation, will make a term that is proportional to the velocity appear in the differential equation. But of course, the issue about causality still remains. And as soon as one look into that issue, it immediately understand that there is something more profound about that problem that has to do with the fact that there seems to be quite an inherent incompatibility between evolution problems like the one that we would like to have for our laws of learning and the solution of variational problems for integral functional. And therefore, in order to tackle this problem, we really need to have some new valid ideas. And so we found that one of the most promising ideas that has been put out in order to make a connection between two words, the words of, as I was saying, evolution problem and variational problem for integral functional, is due to a conjecture by Ennio De Giorgi. Which was investigating, as it is written here in Italian, about the limit of variational problems is in connection to hyperbolic equations. So the equation of classical mechanics are indeed hyperbolic equation. And so in some sense, this conjecture by De Giorgi exactly goes exactly into the direction of establishing a link between variational problems and evolution problem, let's say. And what he did here is to overcome this difficulty by stating that indeed evolution problem cannot be directly derived in terms of a solution to variational problems, but as limit of solution of variational problems. And you see that the limit here is originated by the fact that you are solving a bunch of variational problem, one for each of these f lambda. Now, this conjecture has been proven to be true. So first of all, in 2013, it was proven, the conjecture was proven for variational problems on one dimension, so which depend for function which depends on one parameter, which is actually the things that we're interested into. And then it was also fully proved, I think, 2015 by two other Italian researchers. But since we're interested in the statement for classical mechanics and for, in general, function which depends on one parameter, I will just try to explain the idea in this setting. So the general De Giorgi conjecture is about partial differential equations. So it's about variational problems where the function are of many variables, And the convergence statements is about the solution of partial differential equation. Here, I will try to state the conjecture for just for a function of one variable, which is indeed what we're interested in too. So the idea is the following. So you take this family of functional f epsilon of w that, as you can see, contains the potential, and it contains two terms that depends on derivatives. So these are kind of two regularization terms. One which is proportional to nu, that will be the damping factor, so the term that will go in front of the velocity in Newton's equation, and one will be the mass. This mu will be the mass of the particle in classical mechanics. And then there is this epsilon that have been carefully put in front of these two terms, and an overall factor, which is an exponential factor, which quite very much resemble the exponential term that you put in front of the action in order to include dissipative behavior in your system, but now it has a minus sign here in front of the exponential. And what the Giorgi conjecture is that what you can do is you can, for every fixed epsilon, minimize this functional over this set. So this set is, again, it consists of function in this Sobolev space H2, but in which you give initial condition about position and velocity. Now, of course, each of these minima will have to satisfy a problem that is non-causal in the sense that I'm speaking right now. So there will emerge some boundary condition at the right hand, so at time t, because of its nature, because as I said, is a variational problem for an integral function. But the point is that as you take, so for each of these functional, you find the minimum. That, by the way, Stefanelli proved that if we have some assumption, I would say mild assumption on u, then a minimum always exists. And so you can, in fact, for every epsilon, choose a minimum of this functional. What the interesting thing is that as we take epsilon goes to 0, the solution of this of those variational problems converge to the equation, to the solution of Newton's equation for classical mechanics that we were looking some minutes ago, with this initial condition. So with position W naught and velocity W1. Okay, so this is very nice because first of all, it offers I would say a clearer interpretation of mechanics laws as derived from a variational principle, and then because we can use, of course, this approach, or we hope that we can use this approach to generate, as I was saying, laws that are also suitable for learning. So why do we think that we can do this? So first, some remarks. So the first point are just remark, and of course, it is true that, as I was saying, Newton's law for mechanics already is a viable learning law. I will call it that way. And the other point is really quite nice, is that gradient descent, pure gradient descent, so a first order method, can be just as easily derived from this approach by setting mu equal to 0 in this functional. While if you want to derive a gradient flow, a gradient descent, directly from a variational, from a functional without using this approach is much more difficult, because just if you start with a functional that is an integral functional that contains one derivative, like w dot square, you in the equation of motion, you already get a second order equation. So this approach always also gives a direct and nice interpretation of gradient descent. And the other interesting thing is the fact that at least when t is finite, so we have a finite temporal horizon that in our case is fine, is an acceptable hypothesis, then the approach that, as you may have noticed here, is stated without an explicit temporal dependence on the potential, can be also generalized to the case in which there is a temporal dependence. And in fact, this is one thing that I've discussed in my PhD thesis. And and along with this, it is the fact that using this approach, you see that the potential comes with a plus sign instead of the minus sign that you have in the classical action of mechanics, which might be only a psychological fact, but I think that at least for learning problems, having in the things that you would like to minimize a plus sign in front of it, it is somewhat reassuring. And now I would like to tell you two of the things that I guess are more interesting and kind of motivate all this machinery. So other than this interesting point, one very important fact in this approach is that, as I was saying at the beginning, it makes rather easy to incorporate into this formulation terms which are responsible of enforcing some kind of, let's say, dynamical constraint. So I will show you when I talk about a problem from computer vision that this is the case. So if you have this approach, you can add to these functional terms which you might want to be small, because you have an understanding of the problem, and you know that that combination, that dynamical quantity will help the learning, because it is natural that it should be close to 0. And you can, and with this formulation, you can directly add to the functional. And the other fact is that the variational framework is also rather, I would say, good at handling constraints, hard constraints, hard autonomous constraints, I would say. And if you think about this, you may have also an intuition for what happens in classical mechanics, where you can indeed solve problems where we are constrained on some, let's say, manifold, or on some inclined planes, or in some general trajectories that represent another constraint. And since I would say a lot of a constraint, an autonomous constraint, can be a lot of things. So, for example, think about neural network. Neural networks can be readily expressed in terms of constraint, as you can see here in the picture at the bottom of the slide. The graphical representation of a neural network is just a way just a graphical way of expressing constraints about the variables that one can put on the arcs and on the vertices of the graph. Also, the enforcement of targets, or the input, feeding the network with an input is constrained. And this theory in time, in which you work with quantities that are time dependent, has, as I was saying, it might give you some intuition. As it happened in physics, you can actually compute Lagrange multipliers that tells you what the reaction, the reaction forces should be in order to keep the dynamics on satisfying some constraint. And this can be useful, and in fact is something that we're working on right now, and it seems rather promising. So now let me go to computer vision, and in order to see how of this general principle that I've tried to tell you applies in a practical problem like this. So the specific problem here is the problem of visual feature extraction from a from a video stream, let's say. And in particular, what we want to do is to extract convolutional feature that I denote with this capital phi. And this means practically that we need to determine the convolutional filter that here are denoted as Qij, that goes into the computation of the convolution. Just a note on notation. So on the following slide, if you see some formula in which there are repeated indices, both discrete or continuous, it means that I'm using Einstein convention, summation convention, and so you must think a sum here on J, for example, and an integral here on C. Okay, so how do we want to extract this feature? What is the criterion by which we want to fix this feature? The criterion is an unsupervised criterion that is based on the maximization of the mutual information. So you see here, I am showing you the index, a functional index, which tells you what I want to do. So the first line is minus the mutual information, which is the things that I would like to minimize, since I want to maximize the mutual information. Then you have this purple line, which consists of regularizing terms in space and time. And then the last line is probably the most interesting one, as it is an example of what I was referring previously to as a dynamical constraint. So this is a prototype of the terms that I've denoted as P of TWW dot. And what does this term say? It says is some sort of motion invariance constraint that tells you that I want to find feature that at the end should be consistent with the optical flow. So basically what I would like to end up with is feature that are invariant under motion. So if I predict on some pixel some kind of feature, and then this pixel moves due to the moving of the scene, then for some feature, of course not for all of them, but for some feature, I want that prediction should be consistent with motion. Okay, so what we can do here is to work in a discrete retina. So we can take the convolutional filters, we can discretize it over the pixel of the retina, and then just for my convenience, I would say I like to think of these parameters as a vector, a long vector that consists of all the components of the filters on all the pixel of the retina or the receptive field, if you want, which is this vector Q. So now our variable that in the previous slides was referred to as W now is Q. Q of t is the variable that represent the convolutional filters. And of course, what we can do is to rewrite the functional that previously was called A in terms of this quantity of discretized quantities Q, and we can write down something like this. So again, there is this potential, there's the mutual that contains the mutual information. There is regularization terms that are here in purple, and then there is this dynamical constraint that is a motion invariant constraint that here it is written a little bit more explicitly in terms of the filters Q and Q dot. Okay, so once we have this functional, if we ignore all the caveats that comes from, we have learned from Stefanelli and the Giorgi conjecture and Stefanelli's proof of this conjecture, what we could try to do, and what we have done for some time, is that we could try to look for minima of this functional gamma that, by the way, under some assumption on the potential and some assumption on these parameters in front of the regularization terms exist. For example, on this set where we give only initial conditions. But of course, if we do that and then we trust that these minima are actually much smoother than H2, and we write down the differential condition, what we consistently what we were seeing with classical mechanics, we see we lose causality basically, because other than the differential equation that tells you how the dynamics of Q should be in the interval 0 capital T, we also have at the right-hand side of the interval some relation, some conditions that of course we need to impose if we really want to find a minimum. So we have some non-causality issues. But of course, what we can do now is to use what we learned about variational principle and causality, and try to formulate the problem using the Giorgi approach, and by replacing that functional gamma with this family of functional f epsilon of Q. And here you see that these functionals are, of course, related to the gamma functional, because it has, again, the mutual information here. It has the motion invariance term, which is the one that is proportional to this term here, lambda m, and it has some regularization terms, which some, let's say, higher order kinetic energy, if you want, that depends on Q dot and Q double dot. And then we have the usual and classical exponential factor with a minus sign. And what we can do is exactly what is prescribed by the Giorgi. That is to say, for each fixed epsilon, we can find the minima which exist what we can do then is take the limit epsilon that goes to 0, and what we end up with is some differential equation for Q that I would say is rather interesting, because you can see it has some similarity with gradient descent. With momentum, I would say, since it has this gamma q dot and then this rho q double dot, and it contains the gradient of u. But other than that, there are these terms that are proportional to lambda m, which in some sense should color the dynamics, the gradient descent dynamics, and should move these filters towards configuration that satisfies those that invariance that we would like to have satisfied, that is to say, motion invariance. And notice that indeed we have only initial boundary condition on Q on Q at time 0 and on its velocity at time 0, and we don't have any additional condition at the right hand side. So now, just to and of course there are second order differential equation rather than fourth order differential equation, as you might get directly from the stationarity condition of gamma. So just to give you some idea of the learning curve that we are getting, these are some curve for that functional gamma. Here is called cognitive action during learning. You see it's going down. These 3 lines are 3 different videos. Real videos. Car is a car that is strolling down a road. Matrix is a clip of the Matrix movie, and skater is another clip of a skater that goes on a street. And correspondingly, you see that the mutual information is going up. And another interesting things that we see from this experiment is that the terms that is proportional to lambda m, as you can see from this table, usually improves the transfer of mutual information. So if there is that term, usually the mutual information tends to be higher than if there is not there. So just to give you some reference, if you want to investigate in this kind of things, all the things that relates to vision and that fourth order differential equation, the second order differential equation, motion invariance term, and many more other things, you should look in these 2 first article. While the last article, that is a work that we have written recently, it is mainly focused, excuse me for the pun with words, is mainly focused on focus of attention, and how focalizing attention improves the mutual information, the extraction of information, and gives better results in terms of maximization of mutual information. And this paper will be, it has been accepted at the new RIPS. So if you're going there, you can see in details also this work that shares the theoretical implant that I'm trying to tell you today. So that's all. Thank you for listening. And if there are some questions, I'll do my best to answer.
Okay, thank you very much, Alessandro. That was a very interesting topic, a very interesting talk, obviously.